Okay, everyone, welcome to the Microsoft Research Colloquium. Today we have Tamara Broderick, a professor of computer science and statistics at MIT, and also a longtime friend of mine. We actually have a history of following each other around the country. We were undergrads together at Princeton, and then Tamara followed me to Berkeley for grad school, and then I followed her back to Cambridge to work full-time. And I'm delighted that she's here today to tell us about her work on variational Bayes. So let's give her our attention.
Thank you. You know, actually, on that note, when I was in high school, I went to this science and engineering fair, and my friend Liz Wood told me that I had to look out for this super cool guy, Lester Mackey, who was going to be there. And unfortunately, I didn't meet you there, but then in undergrad, I did. Anyway, so today I'm going to talk about how we can quickly and accurately quantify uncertainty and robustness with variational Bayes. So before I get into the details of that statement, let me just start by talking about our motivating data example in this work. And so we've been looking at microcredit, and so more to the point, our collaborator Rachel Meager, who's a fantastic economist, has been looking at microcredit, and we've been working with her. So if I say anything wrong from the economic side, that's totally me, it's not Rachel. And she's got data on microcredit, these small loans to individuals in impoverished areas, and the hope is to help bring them out of poverty. She's got data from 7 different countries, Mexico, Mongolia, all the way through Ethiopia. And there are a number of businesses at each of these sites, so there's one site in each of the countries. There's between 900 and 17,000 businesses. And so there are a lot of questions that are interesting about this data that basically revolve around how effective is microcredit? You know, is it actually helping raise people out of poverty? But one specific question that you might be interested in is, how much does microcredit increase business profit? And a priori, this could be any real number. You know, it could actually decrease business profit. We don't know. We want to find out if it's actually helping. Okay, so you know, as part of this analysis, figuring out how much does microcredit increase business profit, there are a number of desiderata that we have here. So one is we want to share information across sites. I mean, one thing that I could do is I could just lump all of my data together. I have this data from Mexico, this data from Ethiopia. It's all, you know, in one big data set, and I just analyze it. But that seems sort of problematic. Like, we think that at least, you know, on the face of it, Mexico might be a little bit different from Ethiopia. On the other hand, I don't want to just analyze all the data from Mexico and then separately and totally independently analyze all the data from Ethiopia and then separately and totally independently analyze all of the data in another country because, well, one, I think that there's probably some information about microcredit that can be shared across these countries. And two, you know, if I get a new site in a new country, I want to be able to say something about it. And so I want to be able to share power in a way that doesn't treat these as totally separately or totally the same. And this is something that's very true, you know, not just in microcredit, and I think in general these desiderata won't be just for microcredit, that we want to share this kind of information. We want to quantify uncertainty. So let's say that at the end of the day we find out that microcredit increases business profit by $2 per week. Well, is it $2 plus or minus 1 US cent, in which case, wow, microcredit is definitely helping. Or is it $2 plus or minus $10 or plus or minus $100? You know, maybe it's actually taking people out of business and ruining their lives some percentage of the time. So these would be really, you know, hugely different scenarios where we might have very different approaches after the fact to making policy or making decisions or things like that. And so it's very important to be able to quantify our uncertainty in this application, and also to quantify our uncertainty coherently. So the amount that microcredit increases business profit isn't our only unknown in this case. We also don't know a priori what's sort of the base profit in all of these different countries before we see microcredit. We don't know how these different countries interact, what's their correlation. And so there are a lot of unknowns in this problem, and we want to make sure that when we have uncertainties over them, they don't somehow contradict each other. Okay, so these are 2 big reasons that people turn to something like Bayesian inference. It allows us not only to share information across experiments, but more generally, if I have, you know, some complex physical phenomena, it lets us have these sort of modular graphical model frameworks to build up these complex models. And another big reason to use Bayesian inference is that by using the language of probability, it has inherently a coherent treatment of uncertainty. Okay, so what's the problem? You know, what do we still need to do? Well, we want to get fast results. So in this talk, I'll start with tens of thousands of data points, which we've seen here, and hopefully get up to tens of millions of data points, but these are the sort of scales that we want to be at, and we want to have very quick, fast results so that Rachel Meager or other economists can just turn around and work on their economics modeling and their work there and not have to worry about how long it takes to get the machine learning done. We want to quantify robustness, so something that's really important in any statistical problem, machine learning problem, optimization problem is you're choosing a model. You're choosing a way to describe the universe. And as George Bach so famously said, all models are wrong, but some are useful. And so if I take my model and I change it a little bit, am I going to be making the same decisions? And especially when those decisions could affect livelihoods, they could be very important sort of governmental decisions, we want to feel that they're robust somehow. So we want to quantify robustness. And we want guarantees on quality. We want to make sure that we're actually getting the right answers at the end. Okay, so this is where hopefully this talk will come in. How do we get these fast results? How do we get this quantification of robustness as well as theoretical guarantees on quality? And as I've already mentioned a few times, none of these desiderata are specific to microcredit. This is true of a variety of different modeling scenarios and problems, but this was our motivating example in this particular case. Okay, so let's review Bayesian inference a little bit. So recall that in Bayesian inference, we start with some distribution over our unknowns theta. So theta could be a vector, but as humans, we can only see in 2 dimensions, so I have had to plot this one-dimensional theta distribution. But I have some distribution that recognizes or that represents sort of my knowledge or lack of knowledge of theta to begin with. So one element of theta in this case would be something like, how much does microcredit increase the profits of businesses? And you could imagine there would be other ones like other parts to this vector, like how much does microcredit increase the profit of a business in Mexico, in Ethiopia? What's the base profit of a business in Mexico, in Ethiopia, and so on. So we get a lot of parameters in the end. Then we have our likelihood that describes our data, let's call it x, given our parameter theta. This is another modeling choice. And then finally, Bayes' theorem tells us what do we know about these unknown parameters given the data we've seen, now that we've seen the data x. And so Bayes' theorem, it's just a theorem. It's basically written out right here. And it'll give us some posterior. And the thing that you typically expect to see is that in the prior, things are pretty diffuse. We don't know as much. And after we've seen data, the distribution starts to peak around a particular value, and there's less width to the distribution. We're much more certain that this is the value now that we've seen the data. Okay, well, there are actually a number of challenges to using what at first might seem like a very simple theory in practice. So, you just look at this and you say, oh, I specify my prior, I specify my likelihood, and I get out my posterior, I'm done, data science is solved, we're all good. But in reality, I have to have come up with a prior. I have to have come up with a likelihood, for that matter. These are both choices. In general, modeling is a difficult problem. And so expressing my prior beliefs in a distribution could be something that I find quite challenging for a number of reasons. One, it might be time consuming. Maybe actually we're all perfectly capable of expressing our beliefs about, the effect of microcredit before we've seen any data in a distribution. But, I only have an hour. I've got to leave after this and pick up, something from the grocery store. I've got to go do some research. And so I only have so much time to express my prior, and I'm just going to have to leave it at that. And maybe I haven't fully expressed it at that point. It also might be subjective. Maybe I have some idea about microcredit, and you have some idea about microcredit, and we both think we're reasonable people, and that if we both express those ideas about microcredit, that we'd like to know that we arrive at the same decisions at the end of the day. So we'd be pleased to see that if we start with some range of reasonable priors for whatever of these reasons, that in fact, when we apply Bayes' theorem, we get sort of the same distribution out in the end for the posterior, the same results, the same decisions. We'd be less pleased if, in fact, we applied Bayes' theorem and you came up with a very different decision and set of ideas than I did. This would seem to be problematic. We'd want to go back and either collect more data or rethink our model, or somehow revisit what we're doing. And of course, in modern complex models, where actually these are extremely high dimensional distributions, there are these interesting connections between all of the unknowns, this just becomes more and more problematic. We can't necessarily reason so easily about all of these unknowns in our data set. Okay, so for all of these reasons, we'd like robustness quantification. We'd like to say, hey, if I start with a set of assumptions and I change those assumptions a little bit, how much is that going to change what I'm reporting, the decisions that I'm making at the end of the day? Okay, so now let's say we're totally happy with our prior and our likelihood. Yes?
When you think about robustness, do you mean to sort of like relatively small changes within this space?
Yeah, so this is a great question. So, am I talking about relatively small changes here? You could be interested in two types of things. Global robustness, so over some extremely sort of large set of distributions, or you could be interested in local robustness, which is sort of a more perturbative argument. I think there's also an issue of global robustness is probably a super hard problem, whereas local robustness probably has some linearity to it that we can exploit. And so basically, we're going to come at this from a practical perspective and say, let's use some implied linearity and local robustness to get a sense of that. But ultimately, as a far end goal, we'd like global robustness.
I guess the question that often occurs to me in these contexts is sometimes when you're trying to express a prior, you're expressing it over some space.
Yeah.
But there's other equivalent spaces where you actually may have a stronger and inconsistent prior.
Yeah.
And that tends to be a concern.
So I'll come back to this later, but we're not restricting ourselves to be in a particular like parametric family or anything like that. Yeah. Okay, so first of all, we have this challenge. But a second challenge is, let's say, for whatever reason, we do feel perfectly happy with our prior, perfectly happy with our likelihood. We actually still have to calculate this posterior. And that, in general, is going to be hard. For any non-trivial model that's out there, we actually can't just solve this equation and get this posterior, get this distribution after having seen our data. We have to approximate it somehow. So, for instance, one of the ways that you might approximate it, certainly one of the most influential algorithms of the 20th century is Markov chain Monte Carlo. This gives us a bunch of samples. It's an empirical approximation to the posterior. But problematically, it can be very slow. It'll be right eventually, but you might not have enough time for eventually. And so approximating the posterior can be computationally expensive, and so increasingly we've seen people turn to what's known as variational Bayes, which I'll explain in a moment, but basically you can think of it as something that people have turned to because it's much faster. Now, a problem with variational Bayes, though, is it can underestimate uncertainties. In fact, it can underestimate them dramatically. And so if you're making decisions based on those uncertainties like we talked about before, in this microcredit example, that could be a big problem. You might be, overly confident in your answer when you shouldn't be, when that's not given by the data. And so we really want uncertainty quantification. And so for both of these, for robustness quantification and uncertainty quantification, that's where our methodology, linear response, variational Bayes, comes into play. Yeah?
Is there a specific reason why the uncertainty is always underestimated?
Yeah, I'll explain this in a picture shortly. So the question was, is there a specific reason why the uncertainty, it tends to be underestimated? It isn't actually always underestimated, but we'll see that pictorially in a moment. Okay, and let me just mention really briefly, there's some work by Opper and Winther in 2003 that touches on a very similar idea for uncertainty quantification from a more theoretical perspective. So that's also a very nice paper to check out. Okay, so for the remainder of the talk, I'm going to start by talking about what is variational Bayes as an alternative to MCMC. I'm going to go over this challenge of what's going on. Why is it underestimating uncertainties? How can we correct that? How can we get accurate uncertainties from variational Bayes? And then it'll turn out that basically everything we've been doing here is about perturbation-style arguments. And if you think about it, robustness, as we've described it so far, certainly this local idea of robustness, is all about perturbations. If I perturb my assumptions, how much does that change the output? And so we'll see that this basically gives us robustness quantification. And so again, the big idea here is derivatives or perturbations are somehow relatively easy in variational Bayes, as we'll see. And then if there's time, I'll talk about how there's a remaining challenge with variational Bayes. So here we've talked about uncertainties, but there could be bias. There could be issues in estimating tail probabilities, things like that. And I'll talk about some recent work that Jonathan's been doing on core sets for reliably estimating the posterior in all these different ways. Okay, so what's going on with variational Bayes? Well, let me first tell you what variational Bayes is. Now remember, we're trying to estimate this posterior. Here I've made a slightly more complex posterior cartoon, but of course, I can't draw the really high dimensional, crazy posteriors that we're dealing with in actual applications. That's the kind of thing that we really want to approximate. And so in general, the goal here is we can't calculate the actual posterior, our knowledge of the unknowns given the data, so we need to find some approximation. Let's call it Q star of theta. Now, that's not specific to variational Bayes. This is just sort of the general Bayesian approximation goal. But here's a way that we could go about doing this.
Should I think of this pragmatically? In other words, you want to produce a machine which outputs approximate samples from Q star, or do you want an approximate analytical description?
So before I go to this green blob, it could be either. So samples would, for instance, form an empirical approximation, but you could think of it as a Q star. You could think of it as a measure that puts mass 1 on each of your samples. And so in that sense, Q star is some approximation of P of theta given x. You could think of this as some continuous distribution that's familiar, and that would be an approximation for P of theta given x. At this point, we just want some approximation. We haven't said what particular form that would take. But for variational Bayes, we make more assumptions than that. So for variational Bayes, we'll go a step farther and we'll say, hey, out in the world, there's a set of nice distributions. This green blob represents the nice distributions. Well, what are nice distributions? Well, what are we trying to do at the end of the day? Let's say we're in this microcredit problem. We want to say something like, how much on average is microcredit helping people? How uncertain are we about that value? And so that's something like calculating a mean of a distribution or a variance of a distribution. So I want to be able to calculate means and variances from my distribution. That seems like a nice distribution. Maybe I want to be able to calculate normalizing constants. That's also pretty useful. Maybe these are the sorts of things that I want in life, and so we can imagine that these distributions constitute nice distributions. Maybe you only like to work with Gaussians, so maybe that's your definition of nice. But somehow these are the nice distributions. And the sad fact of life, and the reason that we're even talking, is that unfortunately, the exact posterior is not a nice distribution. Yeah?
In that sense, when you're mentioning what should we have in mind, because I remember from Rachel's paper that she used normal distributions, but at the same time, her variables are something like consumption, these kind of things where, even though they might be normal, they can never be negative, these kind of things.
So this is different. So what you're describing is just actually the description of the model. So you can put together, and it's not even this, it's really the prior and the likelihood. You can do whatever you want for the prior and likelihood. You can basically say, here's a model, here's a description of how the data could be generated. And that's based on, for instance, in the case of Rachel's paper, saying, hey, I have these different countries, and I want them to share power, and I want them to have this particular distribution of the amount that people are earning at each country. And so those are those kinds of choices. The tricky part is once I've made all of those choices, I want to say, what do I know about these unknowns, things like how much microcredit is helping, now that I've actually seen the real data. And that's what P of theta given x is, and it doesn't have some nice simple form. It won't be a Gaussian, it won't be a known distribution. And so for that reason, because we can't calculate this, because we can't just put it in a form, we have to approximate it somehow. So this is like the layer after you've made those choices. Okay, so we have to approximate it somehow. We might want it to be familiar distributions. We might want it to be something. Somehow we want to approximate it with a nice distribution. And as I just said, in any problem of interest, certainly in this problem with the microeconomics data, our true exact posterior is just not a nice distribution. We can't calculate means and variances for it easy. We can't calculate it normalizing constants easily. So we have to do something. And so a natural thing is to say, well, let's look at all of the nice distributions and find the closest. Let's use the closest of the nice distributions for this approximation. Okay, well, now we really have to define what we mean by nice and what we mean by close to make this an optimization problem. If we define closeness to be the callback-Liebler divergence in a particular direction between Q and P, so this is Q star, or sorry, this is between Q, and then Q star will be the minimum of this, the minimizer, and P, our posterior, then we have what's known as variational Bayes. Why callback-Liebler divergence? Is that what you're going to ask? Because that would be great. Yeah. Yeah, great. Why callback-Liebler divergence? Why this direction? It's one particular direction. This is not symmetric. And I think if we're honest with ourselves, it's not because callback-Liebler has beautiful theoretical properties and things like that. It's because it seems to work in practice. So it enjoys a lot of practical success. We can get reasonable point estimates and predictions in some problems. It seems to have been working. We've shown in some work that we can make it work on streaming data. We can make it work on distributed architecture, so we can speed it up to very large data sets. We can run in millions of Wikipedia articles in something on the order of an hour. Yeah?
Someone who believes that the distribution is drawn from there and keeps updating the samples from that will choose that point as well?
I'm not sure I understand the question.
So there's various theorems about how if someone has a misspecified prior and they
Oh,
keep
right.
updating-
Yeah, so that actually just happens to be related to the callback-Liebler divergence, but it's very different from this. So that one's all about sort of, yeah, if you get more and more data, what's going to happen to your posterior. But here we're just choosing to minimize the callback-Liebler divergence to our exact posterior just to get an approximation, not because of some principled reason, just because it's convenient. Yeah. Yeah. Right, okay, so there's a few things here. So one is, could this be problematic in high dimensions? Actually, it could be problematic in many dimensions. So, or in most things you're thinking, it can be problematic in 2 dimensions, as we'll see on the next slide. Part of the problem is that we're optimizing over a set of nice distributions we haven't defined yet. So we'll define that shortly and see how things go wrong. Another issue is, why not use Wasserstein? Why not use something else here? There are total variation, all kinds of distances we have. And I would challenge you to come up with a simple algorithm for those distances. And I think that's why people have used KL successfully in the past, is that it leads to simple algorithms. Yeah?
Now, if you have data where the distribution doesn't have necessarily full support, right? There could be areas where you know the probability is 0.
Yeah.
Then this doesn't work.
So not necessarily, because I could choose my nice distributions to also have no support over those areas. I could choose them to have 0 probability in those areas.
But then you don't have to have intuitions in some way.
Yeah, you would have to know what those areas are and make sure to avoid them. If you don't, then yeah, you'll definitely run into problems. You will very quickly run into problems. Yeah. Okay. So what goes wrong in 2 dimensions and what goes wrong with uncertainty are 2 questions that are on the table that are about to be answered. Okay, let's look a little bit closer at a particular example. This is a super simple example. Let's imagine that we have 2 variables. Like maybe this is the amount that microcredit increases business profit, and this is the amount that we would expect business profits to be in general if microcredit didn't exist. So these are 2 unknowns that we're trying to figure out from our problem, and maybe our exact posterior, even though we don't know it, is a bivariate normal. This isn't realistic. If our exact posterior were a bivariate normal, we would have found it and we would have said it exactly, and we wouldn't have to approximate it in any way. But this will give us a sense of what goes on with variational Bayes. Okay, so with variational Bayes, remember we're trying to minimize the KL divergence between Q and P. So let me write out the particular thing that we're trying to minimize in the particular direction that we're trying to minimize it. Now, what's going on here? Well, as was sort of just suggested in the previous question, let's look at not areas where there's no mass, but areas where there's very little mass. Like right here, there's very little exact posterior mass, P of theta given x. And so if, in an area where there's very little mass, I assign Q to have a bunch of mass, this is going to be like dividing by something near 0. It's going to be huge. This is going to be huge. And we're not going to be minimizing KL with that choice of Q. So we're going to need to choose a different Q. And in general, this is telling us that on a very high cartoony kind of level, our approximation Q is kind of going to be fitting inside of our exact posterior. Okay, to see what actually happens, we still have to say what a nice distribution is. We said what close was. We haven't said what nice is. Well, here's, we think about what makes things nice. What makes it easy to calculate means, to calculate variances, to calculate normalizing constants for distributions? Well, if they were low dimensional distributions, that would be a case where I could probably do that. And so the idea of mean field variational Bayes is to assume that our approximating distribution factorizes into low-dimensional distributions. Just to be clear on the notation here, you can think of each of these as Q sub j. I'm sort of overloading this Q notation. These don't all have to be the same. All I'm saying is that in every sort of variable direction, I just have this totally separate distribution. And so that's the approximation that I'm doing for mean field variational Bayes. Okay, so what if I have axis-aligned distributions, and I'm trying to fit them inside this posterior? Well, here is my mean field variational Bayes approximation, Q star. Now, first of all, you can immediately see what's going wrong with the variance. The width is the variance. It's how uncertain we are about, say, the microcredit effect, how much microcredit is helping. We should be pretty uncertain. We should not be very confident in our results. And we're way overconfident. We're saying, yeah, we definitely know that this is exactly how much microcredit is helping. Let's go make some really important economic decisions based on this. Go team. But it's not at all supported by the data. This is just from our approximation method. Not only that, not only are we underestimating the variance in this case, and in fact, we can do this arbitrarily badly by making this a thinner and thinner bivariate normal, but we're getting no covariance estimates. So if we care about how these variables interact, we're not getting any information about that. Okay, so next I'm going to talk about how we can deal with this. Oh, let me just mention, this is an old problem. People have known about this for a long time with variational Bayes. That has this tendency to underestimate the variance and not give the covariance, but it's also a very modern problem. So to this day, people are saying, I want to do these large-scale Bayesian inference problems. I'm really interested in running on a ton of data, and I tried MCMC and it ran way too slowly, and so I have to run something, and so I'm going to try variational Bayes. And so, yeah.
Is this just coming from the asymmetry in the KL divergence? Or
Yeah, so if you did the opposite direction of the KL divergence, then you would get something that, in this case, overestimates the covariance. Unfortunately, that's not always going to happen in the other direction. The other direction can go both ways pretty easily. It can overestimate and underestimate, so it's just this particular shape that it's definitely going to overestimate. So you can easily come up with examples where it goes the other way. Also, the other direction of the KL divergence turns out to have a lot of issues, practically speaking. In particular, you can see that because here we're integrating over Q, which is nice, because Q is like the nice distribution, so integration with it is pretty relatively easy, whereas integrating over P is pretty problematic. Yeah?
Is the leaf propagation analog of mean field variation Bayes?
I don't know the answer to that off the top of my head. I mean, I suppose you could use mean field variational Bayes as part of a belief propagation.
I mean, there is the bet of the energy, which is a different
Yeah.
information.
But yes, it's like the flavor of combining them.
Yeah, it's
Yeah.
identical to BP, but it's not clear to me that solves the problem.
Yeah, yeah. I mean, so in general, certainly something that you can do is you can avoid like the mean field approximation, but then when you get to higher dimensions, you have this issue of, well, you could approximate with something else, but it won't be nice. And in general, I think the way that people are addressing this right now is twofold. So one is saying, let's have more complex distributions of nice distributions. But this still falls into a lot of the same problem of we don't know if the bias is good. We don't know if the variance is good. Another thing to do is to take Markov-Chain Monte Carlo and say, OK, well, let's throw away some of the theoretical guarantees to make it faster. And Lester's work has been addressing at least, can we diagnose whether that's going wrong or not. But it is problematic that we sort of don't have any guarantees about what's going on there. And so we'd like something that's fast and that we know it's working. And so at least one perspective we could take is instead of taking Markov-Chain Monte Carlo and making it faster by throwing away theoretical guarantees, let's take variational Bayes and make it more correct. Yeah.
So we're talking about the second moment. Are there any guarantees about the first moment?
Yeah, there really aren't. And so that's a big problem. So in fact, it can be biased as well. And so I'd say that we can correct the second moment, in particular based on using knowledge of the first moment when it's reasonable. But this, what I'll be talking about going forward relies on that to a certain extent. And so while we see that in practice, that the point estimates are pretty good, this won't solve that issue. And so that's where that core set stuff that I'll talk about comes into play, at getting actually guarantees on the full posterior approximation. Yeah?
Learning at this point, what is the algorithm for maximizing or minimizing over?
So I'm being agnostic to the actual algorithm for maximizing.
Solve that exactly. You're not approximately solving that.
No, you're actually you're approximately solving it. You're not solving it exactly in general. It could
even
not
minimizing over Q, even though Q is nice, you'll still only approximately.
Yeah, because this is not going to be a convex problem.
Okay.
Yeah, so that's a whole nother layer here. There's so many layers. It's like onions.
But that step you don't believe is problematic. Like even though it's a non-convex problem, you think you're getting.
Oh no, I think that's problematic too. All of these things are problematic, but we do what we can. Yeah. No, I mean, I think all of these things are tough. We want to get these approximations, these good approximations that we can trust to posteriors. And people really are stuck between a rock and a hard place. Like a lot of people are saying, hey, I want to use Markov-Chain Monte Carlo, but I can't on my data set. And so I'll go to Variational Bayes. Both of them very much have an issue about getting stuck in local maxima. So it's not just Variational Bayes, but if you think about the way that Markov-Chain Monte Carlo works is you're exploring the space, and it's very easy to get stuck in something that's locally high probability. So that's fundamentally a hard problem. Okay, so let's at least try to deal with this uncertainty issue. So if we had access to a cumulant generating function, we'd be set, right? So recall that the cumulant generating function is the log of the moment generating function. Why is it the cumulant generating function? Because it generates the cumulants. The first cumulant is the mean, which we get by taking the first derivative of the cumulant generating function and setting t to 0. The second cumulant is exactly the covariance. So we take the second derivative of the cumulant generating function, set t to 0, and we get the covariance. Of course, our whole problem is that we don't have access to this exact posterior covariance. We need to approximate it somehow. Something we could do is we could run mean field variational Bayes, get its cumulant generating function. That exists. Take the second derivative, set t to 0, and now we have v. But v, remember, is our bad block diagonal, bad estimate of the covariance. It underestimates probably the covariance in general and has all these things. And so we'd like a better estimator for sigma. OK, so here's where linear response comes into play. So the idea is let's take the log of our exact posterior and apply a linear perturbation. So we're just going to perturb our exact posterior a little bit. And this is going to define a new distribution. Let's call it p sub t of theta, so long as we normalize, which we haven't done yet. And here's the crazy thing. If we normalize, the normalizing constant is exactly the cumulant generating function. So somehow this linear perturbation contains within it the information of the cumulant generating function. So maybe it's not such a crazy thing to do. OK, and so now I'm going to ask you to imagine something that you would never do in a million years, because it would be impossible. Let's imagine that for every one of these p sub t, and there's a continuum of them, that I fit a mean field variational Bayes approximation q sub t to it. Now, that's an uncountable number of mean field variational Bayes approximations, so you definitely don't want to do it. In fact, you don't want to do more than one. But let's just pretend for the moment that I can do this. So I fit this uncountable number of mean field variational Bayes approximations, q sub t. And I'm going to say to myself, OK, well, I want to approximate sigma. And that's the second derivative of the cumulant generating function. And I can't just take this cumulant generating function and put in q star instead, because that would give me v. So what if instead I take this inner term, this inner derivative, and think about that? Well, that inner derivative is exactly the expectation under p sub t of theta. And if we're willing to accept, and you should be a little bit critical of this, as you already have been in the audience, but if we're willing to accept that this gives reasonable point estimates, that variational Bayes is successful because it gives reasonable point estimates, then maybe we think that the point estimates under p sub t are pretty close to the point estimates under q sub t, and maybe we're willing to make this approximation. So this is the one approximation that we're going to make. Yeah?
Just to confirm, so theta is a two-dimensional vector in this example?
So in this cartoon, it's a two-dimensional vector. In general, it's a d-dimensional vector.
Can you say again what this linear response is?
Yeah, so the linear part is we're making a linear perturbation in the log posterior space. So we're taking the log posterior and we're applying this linear perturbation. Why would we do that? Well, it seems like it contains the information that we want, the covariance. And so that is why we will do that. Also, it'll turn out that we get a really cute formula in the end.
So that's the definition of linear response is the perturbed.
Yeah, is this linear perturbation.
Perturbed log the linear perturbation and then subtracting off the.
Just to normalize.
Yeah, so you have to normalize.
So it is a probability distribution
It's a probability distribution as soon as you normalize.
over theta.
Yeah.
For any fixed t.
Yes, yeah,
Once you fix t, you get a new probability distribution.
exactly.
Over theta. And t is also a two-dimensional vector.
Yeah, t will be the same dimension as theta. And it's sort of describing the size of the perturbation. Okay, and so we're going to call this the linear response variational Bayes approximation of the covariance. Okay, this is a totally unusable formula at this point because it involves this uncountable number of approximations, which we would never do in practice, so let's get rid of that. And I'll basically just say, okay, let's think again about what are the nice distributions. Well, nice distributions are where I can calculate means, covariances, normalizing constants. Sure, you know, low-dimensional distributions are pretty nice, but exponential families are really nice. That's where I can just super easily get all the things that I want. It's a one-stop shop, so let's suppose QT is in the exponential family, and realistically, this is what people do in practice. So if we do that, then we have some mean parameterization, m sub t, and I'll just tell you that after some algebra, we can write that sigma hat, which I had on the previous slide, and I also have right up here. We can get rid of the t. It's the second derivative of the KL divergence with respect to the mean parameterization. And then we can write it in this super simple form. So V is the bad block diagonal covariance that we don't like, but that we sort of get out of mean field variational Bayes just by running it. H depends only on the prior and the likelihood. And I is the identity matrix. And so you can think of this as taking our bad block diagonal covariance and correcting it. Applying some correction, yeah.
Why is this not symmetric?
So it will be symmetric in the end, and you can tell that because this is the second derivative of the KL. It's not as easy to see from this formula, but it's very easy to see from this formula. So it's a valid covariance. It's both symmetric and positive definite so long as we're at a local minimum of the KL. Yeah, these would be concerns.
What is H?
So H is the expectation under Q of the posterior, which sounds crazy because we don't have the posterior, but then we take the second derivative with respect to m. So the normalizing constant goes away. And so it's something we can calculate with like auto differentiation. Okay, so we made one assumption. Everything hinges on this assumption, which may or may not be right. But when it is right, for instance, in this cartoon, or in any multivariate Gaussian exact posterior, it would be exactly right. I mean, this is the only thing that's fully described by its mean and its covariance. Then this would be exact. More generally, it's going to be an approximation. Okay, so let's go back to this microcredit experiment. Remember, we were looking at this microcredit experiment from Rachel Meager with these K microcredit trials. There are a number of businesses at each site. And now we're going to talk about what exactly was the model. What was the choice of the prior and likelihood that was made? And so the model here is to model what is the profit of the nth business at the kth site. So we'll say that that profit is y sub kn. We're going to say that it's normally distributed with some base mean mu sub k. So this is like the profit that would happen on average if microcredit didn't exist, sort of the base profit for this country. Then we're going to have the effect of microcredit. So first we're going to have an indicator variable, whether or not microcredit was applied. This is a randomized controlled trial, so we know whether or not somebody got microcredit. This is totally known. This is not an unknown. An unknown that we do have is tau k. What is the effect of microcredit in this country? How much does it add to the profit on average in this country? And then finally, there's some noise that's specific to the country. Okay, we don't know mu, k, and tau k, where k is the index for the country, so there's a prior on them. We can imagine that there's some global base profit and some global microcredit. And a priori, these might have some interesting covariance, and so here's a covariance for those. And so in some sense, tau is like the most interesting thing here. It's the global effect of microcredit. Is it positive? Is it helping people? Is it negative? What's going on? We want to know about tau. Yeah. So my understanding, and I would encourage you to read the papers, because I believe there's one paper for each of these countries, is that it was a randomized controlled trial for individual businesses on average, and they were giving them microcredit, and then they saw whether or not they randomly assigned each business to receive the microcredit treatment or not, and then they saw at the end what happened. Yeah.
It's these are published papers already run by other experimenters that are published in the biggest economic journals, and they just, I mean, Rachel can download the data from there. They're mostly like MIT professors, so they're like just.
Yeah, if you check out Rachel's paper, there's a citation for every single one of the 7. So. But yeah, it's also publicly available data, which I think is fantastic. Okay, so we'll put a gamma prior on sigma, another prior on mu and tau. We don't know them. And I'll just mention that if you were expecting an inverse Wishart here, a separation in LKJ has some nice properties that an inverse Wishart doesn't, so that's why that prior was used. Anyway, the point here is we have this complex model. We have a number of unknowns. We don't know the effect of microcredit, the base profit in each country. We don't know the overall world effect of microcredit and base profit. We don't know this covariance matrix. We don't know this noise. And we want to know how much do we know about these unknowns after having seen the data. So that would be the posterior. Okay, so first we're going to check, are we getting these means estimated well? And to do that, we're going to compare to Markov chain Monte Carlo as ground truth. So why not just run Markov chain Monte Carlo all the time? Well, in this case, if we use a heavily optimized package for Markov chain Monte Carlo, it takes on the order of 45 minutes. Whereas all of mean field variational Bayes optimization, not even taking advantage of any distributed computing or anything like that, all of the linear response uncertainties, a bunch of sensitivity measures that I haven't told you about yet, but we're going to get to in the robustness part, all of that takes just 58 seconds. And so this can be a real game changer for quickly iterating and working on economic problems. Okay, so we do in fact see, so each of these dots represents the mean of one parameter in the posterior, and we want them to be on this x equals y line, and we see that that's the case. So these are being estimated well. Now we're interested in saying, are we actually getting the uncertainties estimated correctly? And as we might have expected from our discussion of mean field variational Bayes, again, each of the parameters, we're seeing its posterior uncertainty with 1 point, both for MFVB and for LRVB. We're seeing that MFVB is underestimating them, and then LRVB seems to be estimating them correctly.
But anyway, you said the NCMC is not perfect on its own. So why do you say that's the ground truth?
Because there is literally nothing else we can compare to. Yeah.
You run NCMC forever.
Yes, yeah.
But if you ran it for 45 hours, you would.
Yeah. And we found that by running it for much longer, nothing was really changing. Yeah. But yeah, it's a tough problem in these cases because you don't have any true ground truth.
Although if things do line up perfectly, then that's pretty suspicious.
Well, if things line up perfectly, it seems like a good indication that probably both are doing well as opposed to one being a problem.
Well, I mean, if you had a landscape where you had local minima, and
Yeah.
you that both Variational Bayes and Monte Carlo Markov just get stuck in that.
No, that's totally true. And so a big problem in any type of Bayesian inference problem is especially this type of problem, but in much higher dimensions, where you have one local optima and then one that's really far away. And of course, when you're in higher dimensions, it's even much, much, much harder to go from one to another. And that's just a hard problem.
And now Adam's prior is on the left and mine is on the right, and then we never.
Yes, yeah. And I think that that is going to be a fundamentally difficult issue, especially, so one dimension, I don't think this is actually that bad. But of course, we're dealing in much higher dimensions than that. And there it's hard to, in particular, because we don't know normalizing constants. That's the really big issue, because we don't know that mass is missing. If we're in one of these areas, it doesn't tell us that one of the other areas exists.
Does the behavior of the two models two approaches tend to be similar? Like, if there was the same, would they both run into the same problem? Like, could you?
Yeah, it's likely that the minima that they get stuck in would be, or the extrema would be different. Another thing that's mitigating here, and why we don't think that this type of thing would be happening, is that you do tend to get what's known as a Bayesian central limit theorem as you get more data. You tend to get something that is closer and closer to a Gaussian. And in this particular case, because there are hundreds of data points at each of the individual countries, this seems like an unlikely sort of situation. But for more complex models, for fewer data points, it's totally possible.
But I don't have the intuition yet about the spaces, so they're of different types. So the reason to think that they wouldn't get stuck, they wouldn't have the same distribution of local minimas as they have different.
So there are certain types of things that they're doing that are different. I mean, so the optimization problem with VB isn't sort of that it's necessarily just going through and like, with MCMC, it's like you're flipping this upside down, and a lot of the modern MCMC algorithms are saying, oh, this is like a TARP, and I'm just going to move on that TARP. Whereas with VB, we're doing an optimization sort of after taking an expectation over the space and things like that. So it's a little different. Yeah.
If not even sure out of what it, I guess I don't understand how to parse the question, because MCMC I usually think of as operating in the space of values for a random variable, and this thing is operating like in the space of moments.
Well, but sometimes it could be similar, right? So like, let's say I was fitting a Gaussian to this, and I didn't, I might fit it to this one, and that would be a similar behavior to MCMC be getting stuck in this one. Yeah, exactly, yeah. I think there are certain cases where this could go wrong. Okay, so in this, we actually could be making quite a different decision because of this underestimation. So imagine, for instance, we're gathering all these economics experts together, and we're going to decide, is microcredit going to be a thing? Are we going to invest a ton of money in microcredit? We found that, hey, the posterior mean was $3 purchasing power parity. That's positive. Microcredit might be helping people. Maybe we should go ahead with this. And we'll do it as long as the mean is more than 2 standard deviations from 0. And so we look at the posterior standard deviation as reported by LRVB, $1.83 purchasing power parity. The mean is 1.68 standard deviations from 0. And we say, oh, not enough. We need to go back. We need to get some more data. We need to think about, maybe are there certain covariates, certain aspects of businesses that make microcredit more effective? Maybe who owns it? Did they have a business before? Et cetera, et cetera. These are the types of questions that Rachel's, actually asking. This is a simplification of her work. But if we had erroneously guessed that our standard deviation was lower by using MFVB, so in this case, if we had used MFVB, we would have underestimated the standard deviation, in fact, to the point that the mean would be more than 2 standard deviations from 0. And unsupported by the data, we would have said, yeah, microcredit. This is more than 2 standard deviations from 0. Let's go for it. Let's invest in this. So we want to avoid that. Okay, something that you might be concerned about at this point is you might have said, ooh, that matrix inverse looks like a problem. Because I know matrix inversion is, maybe not exactly n squared, not exactly n cubed, but it's between squared and cubed as an operation. And the thing that we're inverting has size number of parameters by number of parameters. And that could be particularly problematic for something like, let's say, clustering. So in clustering, I have one parameter per data point, because I have the assignment of the data point to a cluster. And then I have some global parameters, which are like the cluster locations. And if I have to invert a matrix that's number of data points by number of data points, this is not scalable. Luckily, that doesn't come up. Okay, so we can decompose our parameter vector into, let's call it some global parameters. Again, these are like maybe cluster locations. And some local parameters, these are like assignments of data points to clusters. We can decompose H, we can decompose V in the same way. If we use the Schur complement, we can see that one of our matrix inversions is on the order of the number of global parameters, and we think at least that shouldn't be as bad. But one of them is on the order of the number of local parameters, something like the number of data points. This is potentially a big problem. But let's look at our sparsity patterns. Well, the whole problem with V, the whole reason we even got into this, was that it's block diagonal. And so that's not going to be a problem. This is just going to be block diagonal in N, in the local parameters. H, if you look at H, because in likelihoods you tend to see factors that connect local parameters to global parameters, but not local parameters to local parameters, you'll see that the local parameter part is also block diagonal. And so finally, I minus BH is going to be block diagonal in the local parameters, and so in fact, this inversion will be linear. So that's why that's not totally crazy. Okay, so we've developed this whole sort of perturbation idea at this point. Now let's apply it to robustness, which if anything seems even more natural. Yeah? Yeah.
So I'm wondering why, and yeah,
Right. So I think it's just easier to describe without getting into the covariates, but there's nothing fundamentally different about having covariates in these models or things like this. Yeah. It's just a more complex model. This is like the simplest possible model you could do. So if you look at Rachel's paper, she has sort of a simple model, and then she goes into more complex ones. And so you can do that as well. We also don't want to say anything. Okay, so part of it is we don't want to say too much about the economics problem because we're not the economics experts. She is, and so I encourage you to go to her paper for like the full version of that. Yeah.
Is that sort of homoscedasticity over countries important? Like, is that precisely the sense in which you're letting these experiments sort of?
Yeah. Actually, so if you check out Rachel's paper, you can use the posterior over the heteroscedastic errors to get a sense of how much pooling of information there is across countries. Yeah. Okay, so let's go to robustness quantification. Okay, so robustness quantification, you can think about it as, we could have made a different prior choice. In fact, we could have made a different likelihood choice as well, and the same idea would go through, but just let's look at the prior for the moment. And here you could think of this as one thing, as like, okay, well maybe my prior was normal, and I chose some hyperparameters for that prior, and then I changed them a little bit. But it doesn't have to be like that. It could be some non-parametric change to the prior. Like it could be like, maybe my prior was some crazy distribution, and then I wanted to add some normal noise over here. So this alpha doesn't have to be just like your simple parametric hyperparameter. It could be something much more interesting. And so let's just call our posterior, now when we've very much focused on the fact that we've made this choice in our modeling with alpha, let's call it p sub alpha. Okay, so now we want to get a sense of sensitivity. We want to get a sense of this idea, if I had taken my prior and I'd perturbed it and gotten another reasonable prior, would I get the same results or would I get different results? Well, if you think about it, when we're actually using a Bayesian posterior, we're not really reporting this whole distribution typically. We're reporting something like a posterior functional. In particular, what we've been doing so far this time is we've been reporting a posterior mean. Are we going to say that microcredit has the same average effect or that it has very different average effects under these two priors, these two choices of prior? And so a way to measure sensitivity in this case would be to say, hey, if I look at this posterior mean, like what's the mean effect of microcredit, how much does it change if I change alpha, if I change my choice of prior, if I perturb that? And so we'll call this the sensitivity. And now it turns out, hopefully this looks somewhat familiar to all the work that we did before. If you replace the alphas with t's, this is just exactly what we were doing on that long linear response variational Bayes slide. And the first thing we said was, hey, maybe we think that point estimates are relatively good, so we can replace them with an approximation under mean field variational Bayes. And then maybe we can make this assumption for this linear response variational Bayes estimator in order to actually calculate it instead of having this uncountable number of approximations. We can make this assumption that Q star sub alpha is in the exponential family. In that case, we get another super nice formula like before. So this inner formula was exactly the formula we calculated before. So if we already did all of this uncertainty quantification, correction, this work is done. We don't need to calculate anything else. B comes from the form of the prior. If it's conjugate exponential family, this will be the identity. Or generally, we can calculate this with automatic differentiation. A comes from the form of G. If G is the identity, if we're calculating a posterior mean, this will be the identity. Okay, so again, let's look at this model, and we could say to ourselves, ooh, there were a lot of choices here. We had to choose this gamma A, B. We had to choose eta, C, and D for the separation in LKJ prior. We had to choose this lambda inverse. We had to choose, well, we didn't have to choose C. We had to choose mu naught and tau naught. And even if you're like some super microcredit expert like Rachel Meager, there's probably still some range of reasonable values that you think might be okay. And you want to know that over that range, your decisions wouldn't change. So we can check if that's true.
Can you repeat that? So you're like, it's variational in the sense of the prior, like of mu naught, tau naught, not in the sense of distributions of changing normals to something different.
So there's a few things. So basically, let's look, for instance, at this normal. So this normal is we're saying, here's our prior on mu and tau. And maybe we believe super strongly that this is our prior on mu and tau. This is definitely what I know about mu and tau going in. But maybe, actually, I talked to my friend who's also a super microcredit expert, and they would have come up with this prior. It's so close. Is it going to give me different results? Is it going to give me the same results? I'd like to know. In particular, at the end of the day, we're making some kind of decision like, is microcredit helping people? Is the posterior mean more than 2 standard deviations from sigma? And if it is, then maybe I'll go and invest in this. And if it's not, I won't. And so I want to know that if I change my prior, would I have changed that decision? So that's the kind of question that we're asking. Now, I'm going to formulate this in terms of if we change these hyperparameters, would I change that decision? It doesn't have to be this parametric decision. It actually could be non-parametric. Yeah? Right. So this is exactly, so if you take something like the hyperparameters and just change them, then you can just think of this as a derivative with respect to the hyperparameters. More generally, if you wanted to do something like, say, here is my prior, and then I want to change it by, maybe adding a normal and normalizing it. Then I could say that alpha is sort of the amount that I'm doing the weighting between the original prior and the normal, and I could take a derivative with respect to that alpha. Yeah, basically. As long as you can formulate them in a way that there is an alpha that you can take a derivative with respect to, then you can make that change. But just the one thing I want to emphasize is that it doesn't have to be some parametric family form that you change.
But then is that approximation still a good one? That near alpha equals 0, we really have a good...
So it's not near alpha equals 0. It's near alpha, your original choice in this case. So it's a little bit different than the t case. So it's near change in alpha equals 0, like delta alpha.
No, but I meant if you do this thing with the Gaussian, then what would you do here? Which point would you use this approximation?
Right. So in this case, it would be near alpha equals 0. Yeah, in that case, as opposed to in the case where other cases it might not be.
But
Yeah.
then it's not so clear, given how drastic you actually change by going from this one to a Gaussian.
So I would say that locally, you don't expect things to be too different. But yeah, as you turn this into a normal, eventually you're going to lose the linearity of the approximation. It's true. But I still think that if you want some notion of robustness, this is an easy one to get. It's an easy one to calculate. It's one that you can calculate quickly and sort of with minimal fuss on your computer. There's a sort of a nice formula. And so it's a step in the right direction. Ultimately, we'd like to have a global sense. But I think that's a hard problem. But maybe someone can solve it. OK, so let's just go ahead and see what this looks like. Again, the assumption we make is that the means are well tracked, and we have that. Let's consider a particular perturbation. And what we'll do is we'll just run mean field variational Bayes for one value of the hyperparameter. We'll run MCMC for one value of the hyperparameter and another one just to see if mean field variational Bayes is, if LRVB is tracking that. And we see that it really is. And again, with LRVB, we're not getting it in just one direction. We're getting it in sort of all directions simultaneously. OK, again, just to see how this might affect us, we could calculate the sensitivity of the microcredit effect with normalization to be on the scale of tau standard deviations, because that's sort of the interesting thing at the end when we're making this decision, is microcredit helping people. We can get sensitivities for all these parameters, all these hyperparameters. It's interesting to see that they're on very different scales. And now let's go back to our original thought experiment. So we said that the mean was less than 2 standard deviations from 0. So we weren't going to like make microcredit our new policy. And then let's say that we perturbed one of these parameters by 0.04. We thought that was totally reasonable. You know, we talked to our economist friend, and they said that that would have been a totally fine hyperparameter to start with. And we found that now the mean is more than 2 standard deviations from 0. Now, in this direction, that doesn't really mean anything. We already weren't going to fund this, and so we still won't. But you can imagine this going in the other direction. You know, that maybe we started our analysis, we found that the mean was more than 2 standard deviations from 0. We high-fived everybody, and we said, OK, we're going to fund microcredit. It's super awesome. And then we did this robustness analysis, and we found that for perfectly reasonable values of the hyperparameter, the mean is not more than 2 standard deviations from 0. And so we'd be more conservative. We'd go back. We'd get more data. We'd think about our covariates affecting this, things like that. OK, so I will mention, I phrase this in terms of mean field variational Bayes, but there are a lot of other types of variational Bayes besides this, and this isn't specific to mean field variational Bayes. It can be applied to other types of variational Bayes. And since I am running out of time, I'll encourage you to talk to Jonathan, who is interning here anyway, about his core sets work. But basically, a number of people brought up some issues with what we've been talking about. So what about bias? Variational Bayes could be biased. What if I care about a long tail or some other interesting things that could be going on? I want something that's fast, but is also going to give me a good posterior approximation. And so this core sets work is getting at that by using a data summarization approach. Let me just skip ahead to the end. OK, so this linear response idea lets us get these covariance estimates as well as this robustness quantification. And while this core sets work, I think, is really great in terms of getting us fast, approximate Bayesian inference that also gives us theoretical guarantees on quality, I think there's still a place for these two ideas to come together. I mean, this perturbation idea for robustness, robustness quantification is something that people want and should have in their analyses. In a lot of these analyses, you want to know how robust these sometimes arbitrary or at least semi-arbitrary choices that you made, how robust your outputs are to these choices. And this is true for any type of modeling, but for Bayesian inference, this seems to be a way to do it. And so combining this with a way to actually get reliable inference with theoretical guarantees, I think, is going to be very powerful. And so if you're interested in any of these ideas, I'd love to chat more after this. And I'll just point out our papers on this. So there's a NIPS 2015 paper on the linear response methods for covariance estimation. Our robustness paper is in preparation. Hopefully it will be out soon. And this NIPS 2016 paper is on the core sets work if you want to read up on that as well. Thank you. Yeah.
On slide 9, you showed the y equals x line comparing the MCMC results to your results.
Yeah.
And there was one point near the bottom that on a relative scale, they were pretty different.
Oh, yeah.
Do you know what happened there?
Yeah, so I mean, I suspect that, so all of this relies on the bias being 0, and so probably the bias was not 0 for that point. So if the bias is 0, then everything is exact. There's no approximation. And so that's pretty much got to be the culprit.
I guess it could be the MCMC also.
Oh, that's also true. I actually pretty much, so we use Stan. I think Stan is pretty trustworthy on this problem. I lean towards it being LRVB. It's possible it was the MCMC.
Stan is pretty much built to do the solve this problem well.
Yeah, yeah.